Students, we're going to make 4 videos, and this is the very first of that kind. In each of these videos, we're going to come out with the doubts of the subject that you have been asking, those many questions as queries which most students have been asking us through email. We've got a lot of response of students who are asking their queries in physics and chemistry and biology and maths. These are the popular questions. These are those questions in which students have maximum doubts. So what have we done? We have taken all the questions, we've given it to our moderators and the teachers, and these teachers and the moderators are going to give the solutions of the most probable questions. These teachers and the moderators are going to solve your doubts live right now. Exactly from this point in time, I'm going to pass on this camera to the teacher, and the teacher is going to solve the most asked questions for you. Are you ready?
On introducing a thin sheet of mica of thickness 2 micrometer and refractive index 1.5 in the path of one of the waves, the CBF shifts by n fringes. If the wavelength is 5000 AU, then n is equal to dash. So I have Ri as 1.5, thickness T 2 into 10 raised to minus 6 meters, wavelength lambda is 5 into 10 raised to minus 7 meters. Then the shift is given by the formula. Shift is equal to W by lambda mu minus 1 into thickness. Now here they have said the shift is also given as n fringes. N fringes means NW. Therefore, NW is equal to W by lambda into mu minus 1 into thickness. So W and W cancels. N is equal to 1 upon 5 into 10 raised to minus 7 into 1.5 minus 1 into thickness is 2 into 10 raised to minus 6. So this will work out to 1.5 minus 1 is 0.5 into 2 into 10 raised to minus 6 upon 5 into 10 raised to minus 7. So this will become 1 by 5 into 10. So that is 2. So the answer is 2. In a given arrangement of the meter bridge, the null point is obtained at a distance of x from A. If the diameter of the wire AB is doubled, the null point from A will be dash. The choices are 2x, x, x by 2 and 3x. Now this is our diagram. This is the wire AB is the potentiometer wire, R1 and R2 are the resistances. We are getting null point x. Now what they are telling us is the diameter of this wire AB is doubled. So how much will be the shift in the null point? Now the null point does not depend upon the area of cross section, nor does it depend upon the thickness. So here the answer will remain x. MCG shunted by a resistance S, the current capacity is increased n times. If the same galvanometer is shunted by another resistance S dash, the current capacity will be increased by n dash, which is given by dash. Now, our general formula for shunt is S is equal to G upon n minus 1. This is the shortcut formula for the shunt resistance. Now here they have said when the MCG is shunted by S, the current increases n times. So G upon n minus 1. Similarly, when it is shunted by S dash, the same galvanometer, so G, the shift increase in the current is n dash minus 1. Now what we do is, we divide S upon S dash, which will give me G upon n minus 1 into n dash minus 1 upon G. So S upon S dash will be equal to n dash minus 1 upon n minus 1. Now we want it in terms of n dash. Therefore, S into n minus 1 is equal to S dash into n dash minus 1. So Sn minus S is equal to S dash n dash minus S dash. So S n minus 1, which is a common here, will be plus S dash is equal to S dash n dash. Therefore, n dash will be equal to S n minus 1 plus S dash upon S dash. So our answer is this. Here there is a common question which is asked in many exams. It says that there is a resistance R and there is a slider of resistance say small r which is moving with a velocity v in a magnetic field which is perpendicular to its length. Now what does this signify? So there is a conductor whose length L, or what we called it as a slider of length L, is moving, so it will act as a battery or a source of EMF. So my diagram looks like this. This is R, this is the cell, and this is the resistance of the wire R. So an EMF is induced in it, and this EMF is given by the formula E is equal to LBV. So my diagram will become the source E and the resistance capital R and small r are in series. So electric current I will be equal to E upon R plus small r. So I is equal to E upon R plus small r will become LBV upon R plus small r. So the current is LBV upon R plus small r. You can get a lot of problem based on this. One such problem is what we are discussing. Here we are having a similar problem based on what I discussed earlier. The problem reads: the rectangular loop with a sliding conductor of length L is located in a uniform magnetic field capital B perpendicular to the plane of the loop. The conductor has a resistance capital R. The sides AB and CD have resistances R1 and R2 respectively. The current flowing through the conductor due to its motion to the right with a velocity v is given by the following choices. Now what does this look like? So I am having two resistance R1 and R2 with a slider whose resistance is capital R. So my diagram will be, this is R1, parallel to this is R2, and the slider which is moving with a velocity will act as a source and its resistance is R. Now this source will have EMF E is equal to LBV as discussed earlier. So this resembles an equivalent diagram which is RP, R1 and R2 parallel RP, and series with this is your R. Now resistance parallel will give me R1 R2 upon R1 plus R2, that is product upon sum, and series will be RS will be equal to RP plus R. So the current I will be E upon RS, which is equal to LBV upon RS, that is RP plus R. Therefore I is equal to LBV upon RP is R1 R2 upon R1 plus R2 plus R. So when you solve this, this will become LBV upon R1 R2 plus R into R1 plus R2 upon R1 plus R2, that goes here R1 plus R2. So my choice will be out of this BLV R1 plus R2 into this. So this is our choice. Hydrogen atom is in an excited state of principal quantum number n. It emits photons of wavelength lambda and returns to the ground state. The value of this n is dash, and the four choices are given here. Now we know the wave number is given by 1 upon lambda is capital R, Rydberg's constant, into 1 upon nf squared minus 1 upon ni squared, where nf is the final state and ni is the initial state. Now here they have said initial state is n and the final state is the ground state. So my ni becomes n and nf becomes 1. Therefore 1 upon lambda is equal to R into 1 upon nf is 1 squared upon 1 upon initial is n squared. So 1 upon lambda R is equal to 1 minus 1 upon n squared. So 1 upon lambda R minus 1 is equal to minus 1 upon n squared. So 1 upon n squared is equal to 1 minus 1 upon lambda R, which is equal to lambda R minus 1 upon lambda R. So n squared is equal to lambda r inverted lambda r minus 1. So n is equal to under root lambda r upon lambda r minus 1. So the choice is A. When an electromagnetic radiation of frequencies 5 into 10 raised to 15 hertz and 8 into 10 raised to 15 hertz falls on the same metal in two different experiments, the ratio of the kinetic energy of the electrons liberated is 1 is to 3. Then the threshold frequency of the metal is dash. And the choices are given here. Now we know the kinetic energy is given by h into nu minus nu 0. So I am given the ratio of kinetic energy 1 is to 3. So kinetic energy 1 upon kinetic energy 2 is equal to nu 1 minus nu 0 upon nu 2 minus nu 0. So this is 1 is to 3 is equal to 5 into 10 raised to 15 minus nu 0, 8 into 10 raised to 15 minus nu 0. We cross multiply, so this will become 8 into 10 raised to 15 minus nu 0 is equal to 3 into 5 into 10 raised to 15 minus nu 0. So this is 8 into 10 raised to 15 minus nu 0 is equal to 15 into 10 raised to 15 minus 3 nu 0. So this will become 2 nu 0 is equal to 15 minus 8, 7 into 10 raised to 15. So nu 0 is equal to 7 by 2 into 10 raised to 15. So nu 0 is equal to 3.5 into 10 raised to 15 hertz. Such a choice is this. A monochromatic light of wavelength lambda is incident on an isolated sphere of radius small r. The threshold wavelength of the metal sphere is lambda 0. The number of photoelectrons emitted before the emission stops is dash. Now here the number of photons emitted before the emission stops refers to the stopping potential. So my formula will become EVS, stopping potential, is equal to kinetic energy max is equal to HC into 1 upon lambda minus 1 upon lambda 0. So stopping potential Vs will become Hc upon E into 1 upon lambda minus 1 upon lambda 0. Now potential for a sphere is given by 1 upon 4 pi epsilon 0 charge upon the distance, that is the radius here. Also charge is quantized, that is Ne, Q is equal to Ne. So V will become Ne upon 4 pi epsilon 0 r, which is equal to Hc upon E into 1 upon lambda minus 1 upon lambda 0. So number of photoelectrons emitted N will be equal to Hc into 4 pi epsilon 0 r upon E squared to 1 upon lambda minus 1 upon lambda 0. So my choice will be RHC 4 pi epsilon 0 upon E squared, that is C. Electron in a certain energy level n is equal to n1 can emit 3 spectral lines. When they are in another energy level n is equal to n2, they emit 6 lines. The speed of the electron in the two orbits are in the ratio dash. So the number of spectral lines emitted is given by n2 minus n1 into n2 minus n1 plus 1 upon 2. This is the formula where n2 is the initial state and n1 is the final state. So in my first case, the electron in a certain energy level n2, which is equal to n1, is emitting 3 spectral lines. So 3 is equal to n minus 1, that is coming to the ground state, into n, this is n1 minus 1 plus 1, so 0, so upon 2, so this is 6 is equal to n1 squared minus n1, which means n1 squared minus n1 minus 6 is equal to 0, which is a quadratic equation. Upon solving this, you will get n1 is equal to 3 or n1 is equal to 2 minus 2. So what I take is the value n1. Now similarly 6 is equal to n2 minus 1 into n2 upon 2. So 12 is equal to n2 minus 1 into n2. So 12 is equal to n2 squared minus n2. So n2 squared minus n2 plus minus 12 is equal to 0. Again this is a quadratic. So 4 3s are 12. So n2, when I solve this, I will get n2 is equal to 4 or n2 is equal to minus 3. So I take the positive value. Now velocity ratio is what they want. Now V is inversely proportional to the principal quantum number. So V1 upon V2 will be equal to n2 upon n1. So 4 by 3. So our choice is this. The intensity at a point where the path difference is lambda by 6 is I. If I0 denotes the maximum intensity, then I upon I0 is dash. The choices are given as follows. Now for path difference as lambda by 6, so path difference, which is say x, is equal to lambda by 6. Then the phase difference is given by the formula 2 pi x by lambda. So that is 2 pi lambda by 6 upon lambda. This will give me pi by 3, that is 60 degrees. Now for 60 degrees the intensity I is equal to say a squared plus 2aa into cos of 60. So that is a squared plus 2a squared into 1 by 2 will give me 3a squared. Now similarly for maximum intensity, so for maximum intensity the phase difference delta will be 0 degrees. Therefore intensity I0 as given in the problem, I0 denotes the maximum intensity. So I0 is equal to again R squared resultant squared. So that is a squared plus 2aa cos of 0. So this is a squared plus 2a squared gives me 4a squared. Therefore I upon I0 will be 3a squared upon 4a squared. The answer is 3 by 4. Waves from two sources overlap each other at a point. The amplitude and frequencies of these waves are same. The ratio of the intensities of the two waves when they arrive in phase to that when they arrive 90 degrees out of phase is dash. Choices are given as follows. Now for the waves arriving in phase, the phase difference delta is 0. Therefore say intensity I1, which is equal to R squared, will be equal to a squared plus 2aa cos of 0. So this comes to 4a squared. Now phase difference delta when 90 degrees out of phase, say I2 is equal to again R squared is equal to a squared plus 2aa cos of 90. So intensity 2 will become 2a squared. Therefore I1 upon I2 is equal to 4a squared upon 2a squared is 2:1. So answer is 2:1. A straight conductor of length pi squared meter is carrying a current of 2 amperes. The magnetic field is measured at a distance of 1 centimeter from it. If the wire is now bent to form a circle of radius small r and carries the same current as before, then the ratio of the magnetic field at the center to that obtained in the first case is dash. Choices are 50:1, 1:50, 1:100 and 100:1. So my data tells me length is equal to pi squared, current I is 2 amperes, distance D is 1 into 10 raised to minus 2 meters. then the magnetic field due to the straight conductor, say Bs, is equal to mu 0 I upon 2 pi d. Now the same wire is bent to form this circle of radius small r. So length is equal to pi squared is equal to circumference, that is 2 pi r. So r is equal to pi by 2. Now magnetic field at the center of the circular coil is given by B is equal to mu 0 I upon 2r. Therefore the ratio is what they have asked. The ratio of the magnetic field at the center to the magnetic field from the straight conductor, say Bs, is mu 0 I upon 2r into 2 pi d upon mu 0 I. Now mu 0 I cancels, 2 and 2 cancels, so the ratio will be pi d upon r. So pi into 1 into 10 raised to minus 2 upon r is pi by 2, so this goes up, pi and pi cancels, so 2 by 100, that is 1 by 50. So answer is 1 by 50.
So this is the end of this mega doubt solving session. I'm sure you must have benefited, and I'm sure you must be having more questions regarding this video that you saw. You may be having more questions other than the questions which the teacher have dealt with. All you can do is write to us at care@meritstore.in, and we will be so happy to take all your doubts, accumulate it, and put it in another video and share with you wherever you are. Thank you for your immense love and support. Continue supporting Umang Foundation Trust with a small donations of whatever you want. You can do 20 rupees, 10 rupees, 50 rupees, whatever. Donate your old books, clothes, whatever you can give to those many children across the city and country. And if you're in Bombay, come down to our center and help these children learn and grow and become something. All the very best. Write in with your doubts.